Alright, so we're going to talk today about properties of definite integrals. So moving forward with integration, we're going to be looking at what happens if we're exploring integrals in the limit, as in terms become infinitely small and the number of rectangles get closer and closer to infinity. As in, we just keep adding more and more rectangles and we make them smaller and smaller. We're going to have to look at some geometric functions today that might also contain negative values. When we're graphing them, that means they go below the x-axis, as well as positive values above the x-axis, and then possibly some zeros. Now, first, what do we do if we're dealing with negative area? So at times, we're going to integrate functions that go below the x-axis, negatives, and that's fine. Here are some tips for when that happens. If the area is below the x-axis, it counts as negative area, meaning the total area between two endpoints for a curve is really a net area, where the total area below the x-axis and above the curve is subtracted from the total area above the x-axis and below the curve. So now let's look at what definite integral notation looks like. So way back when Leibniz introduced a notation for the definite integral, it's a Greek letter, or it represents Greek letters of summation become letters in the limit. So in that summation notation we looked at in the last lesson, we can rewrite that in the following notation, where it's read as the definite integral from a to b of f of x with respect to x. Now there are some parts to these definite integral notation. This b right here, that is called our upper limit. And then this s-looking symbol, we call that the integral. A is our lower limit. F of x here is a derivative. We also call that the integrand. And then dx is a variable of integration. We'll just call it x. The entire thing, all of that, we call the definite integral. Now, we can also say that the definite integral can be used to determine the following: the net area, or distance traveled, bounded by the x-axis, the function, and vertical lines at x equals a to x equals b. So now let's look at properties of definite integrals, which in our note packet, they come after example 1, but they're going to be really handy when we're doing example 1. So Properties of definite integrals. So the definition of the definite integral of f on an interval from a to b just specifies that a is less than b. Now, however, it's also convenient to extend the definition to cover cases in which a is equal to b or a is greater than b. So if f is defined as x is equal to a, meaning our upper and our lower limit are the same, then the integral in that case is just going to be 0. And then we can also say if f is interchangeable on a to b, then the integral from a to b of the function is equal to, let me rephrase that, the integral from b to a of the function is equal to the opposite of the integral from a to b. Now, we also have this additive identity property. So if we take and say f is interchangeable on 3 closed intervals, we call them a, b, and c, or those intervals can be determined by those numbers, then the integral of a to b is equal to the integral from a to c plus the integral from c to b. Then we've also got properties of definite integrals. If f and g are interchangeable on our interval and k is a constant, then the integral of, say, a scalar multiple from a to b of k times the function is just going to be k times the integral of the function. And then the integral of from a to b of just k is going to be k times b minus a. And the integral from a to b of f of x plus or minus g of x is equal to, we forgot to put an equal sign in here, so right there we need to add an equal sign. The integral from a to b of f of x plus or minus the integral from a to b of g of x. So now let's look at example 1. So we are going to use this graph to evaluate each of the following integrals. Note that the graph consists entirely of line segments and a semicircle from -8 to 13. So our first example we're looking at is the integral from 0 to 7 of f of x with respect to x. So from 0 to 7, we're looking at this region right here under the curve, which is above the x-axis, which means we're going to have a positive area. Now we need to find the area of that, and that shape is a trapezoid. So just as a reminder, to find the area of a trapezoid, trapezoids have 2 bases, so we're going to first add them, and then we can multiply by the height of the trapezoid and divide everything by 2. So in this case, we've got one base that is 3 and another base that is 7 with a height of this trapezoid that is 4. So we are going to go 3 plus 7, multiply that by 4, and divide that by 2 to find the area there. 3 plus 7 is 10 times 4 divided by 2. 10 times 4 is 40. If we divide that by 2, we find that the area under the curve is 20. Let's check out number 2. We're looking at the integral from 0 to 13 of the function with respect to x. So we know that's going to include the part we just found, the 20, and it's going to include this part that's under the curve. So we're going to go 20, and since the next part is under the curve, we're going to subtract the area of that trapezoid. So that trapezoid has a base of 3, a height of 3, and another base of 6. So we're going to go 6 plus 3 times 3 and divide that by 2. Well, 6 plus 3 is 9, and 9 times 3 is 27. If we divide that by 3, we're going to get 13.5. So if we subtract 13.5 from 20, we're going to find that the net area is 6.5 square units. Now let's look at 3. We're looking at the definite integral from -6 to 0 of our function with respect to x. So that part is this semicircle. Now, as a refresher, again, the area of a circle is found by pi times the radius of the circle squared. Here we have a semicircle, so we just have to divide that by 2. To find the radius, we can just take the diameter, the distance across the circle, and divide that by 2. Our current diameter is 6, so halfway across that is going to be 3. So we're going to take pi times our radius, 3, squared, and divide that by 2. So we're going to get 9 times pi over 2. Now, because this area is below the x-axis, we do have to make it a negative area. I'm totally fine with you leaving it as negative pi over 2 because that is a very exact answer. You could also plug it into the calculator and get a decimal answer. I will take that as well. Part 4, we're taking the definite integral from 3 to 3 of our function with respect to x. This uses one of those properties where the bounds are the same, so the answer is simply going to be 0. Let's look at 5, part 5. We're looking at the definite integral from 7 to 0 of our function with respect to x. Well, we've got the same bounds, and it's just we switched them from question number 1. Question number 1, we got an answer of 20. The properties say if we switch the bounds, we just take the opposite value. So we get negative 20. In a way, you can kind of think of it as like going backwards. So number 6 now, we're taking the definite integral from 10 to 4. So we're taking this part and this part, which again are 2 trapezoids. So let's find the area of each trapezoid. Oh, and this is of our function with respect to x. Utilizing those properties, we know that this is the opposite of the integral from 4 to 10 of our function with respect to x. So if we just find the integral of our function with respect to x from 4 to 10, we take the opposite of that, we'll be good. So from 4 to 10, we've got a base of 1 and a base of 3, and then a height of 4. So we're going to go 1 plus 3 over 2 times 4. So we're going to get 4 times 4 over 2, so we'll get 8. We're going to take the opposite of all of this. Minus, we've got another trapezoid with a base of 3 and 2 and a height of 3. So we're going to go 2 plus 3 times 3 over 2. Well, 2 plus 3 is 5. Times 3 is 15. If we divide that by 2, we're going to get 7.5. 8 minus 7.5 is 0.5, which means the area, or the answer to this question, is going to be negative 0.5 or negative 1/2. Let's just do a couple more of these, like question 7 or part 7. We're going to find the integral from negative 8 to 13, so the total area of our function with respect to x. So we've got a few different shapes here. We've already found the area of the circle and the two trapezoids, but there is here another shape. We've got a triangle. And as a reminder, area of a triangle is base times height divided by 2. So we're going to first find the area of the triangle. Base is 2 times height 4 divided by 2 minus the area of the circle 9 pi over 2 plus the area of the next trapezoid 20 minus the area of that last trapezoid, which is 27 over 2. We'll leave it as a fraction. So 2 times 4 is 8, divided by 2 is 4, which maybe for purposes of the adding and subtracting, let's leave it as 8 over 2 minus 9 pi over 2 plus 20 would be 40 over 2 minus 27 over 2. Now, I'm totally fine with just combining parts that don't have pi yet. So if we went 8 plus 40, that's 48. And if we subtract 27 from that, we get 21. So 21 over 2 minus 9 pi over 2. Well, 21 over 2, we can just write it as 10.5. So our answer we're going to give is 10.5 minus 9 pi over 2. Now, I'm also fine with you giving an approximate answer. So you could put 9 pi over 2 into your calculator and just bring this down to one single number. So now we're going to actually skip numbers 8 and 9. And we're going to go right to 10 if you're using your note sheet, which says to find the average rate of change in f over the interval 0 to 5. So we're going to take f of 5 minus f of 0 over 5 minus 0. Well, f of 5 is 4, and f of 0 is 0, so we're going to go 4 minus 0 over, well, 5 minus 0 is 5, and 4 minus 0 is 4, so the average rate of change from 0 to 5 is 4/5. Now the very last thing we're going to do in this video before we move on is we're going to look at question 11 on this page with example 1. It asks us, true or false, is the integral from 0 to 2 of the function with respect to x plus the integral from 2 to 4 of the function with respect to x equal to the integral from 0 to 4 of the function with respect to x. Utilizing the properties, this is true. So we'll finish our examples in our next video.